All right, 9 o'clock. So time for us to start. We're all at home again. We'll see. I have no idea. We'll see how long this lasts. Maybe we'll be back on campus soon-ish. Maybe not. Yeah, about the homework, there were a number of people who didn't follow the instructions for the homework, the PDFs, not like photos, and also combining them into a single file, not multiple files, or the rotating. We wrote some comments for some people, told them like, really, we shouldn't have to be doing that. As things are going, there's certainly a possibility, at least half of you definitely will be doing the exam online because you're not in the country. And those of you who are here, we don't know. But in preparation for that, you need to be following those instructions and using the scanning app, even if you're doing your work on just one page. Midterm is going to be multiple pages. If you're submitting multiple files and giant images, it becomes an absolute nightmare for me to try to sort out and organize. So single file as a PDF from everyone. We are not going to accept other things. You have to show me that you understand that and you know how to do that. And you've learned how to use a scanning app, because we are going to need that skill in the future. Okay, homework will be returned probably by the end of today. Where 2 of the sections are finished grading, just 1 more to go. Some people had some trouble with the matrices part and got a bit confused about just how to do them. So I'll probably make a video. Like, we've done a bunch of examples. Not many people came to the workshop, but the recording is up, so you can go and watch that and see a whole bunch more examples. I might make another video just talking about the solutions to these particular questions as well. Anyways, this week, we are going to talk about systems of inequalities, just briefly, some concept things there. And then move on to starting to talk about a thing called linear programming. So sort of the simplest type of optimization problem that we might see. We won't quite get to a full real linear programming question, but we'll be close to it, and then we'll take that final step on Thursday in the next class. Okay, so we'll do 1 application question with matrices just to review. We'll talk about some graphing with systems of equalities. I'll repeat what I talked about in that little extra video and like very briefly with you guys in the previous class, and then also what you did for the preview question. And then we'll go on to our linear programming question. All right, so just reminding everyone, these are the operations that we are allowed to do for matrices, just like doing regular, quote unquote, regular elimination here. We can multiply by a constant, We can add and subtract one equation from another one. We can add and subtract one row from another one. One key difference is that we are replacing one of the rows with the results here. And we can change labels on rows or swap the rows. Both of those are the same thing. All right, so let's see if we remember our process. We talked about some shapes. So let's say we start off with this and we have a box. What is my first goal if I'm going to do elimination using a matrix?
To get a triangle.
Triangle shape. Okay, so that triangle will look like this. How will I get there? What do we do to make this triangle shape?
make the middle left number a 0, and then the one below it a 0, and then the one on the middle bottom a 0.
Okay, so we're going to kind of choose one of the columns. Let's say we start with the X column. We'll choose one of the positions and say, okay, this is the one I want to use here. So often, not always, I would get a 1 here, but not critical. The main thing is I use this position to say, okay, eliminate this, eliminate this. I want those to turn into zeros and just disappear. And then I go one step over to the left. Here's my next position in this main diagonal, and I eliminate everything below. So I have zeros below the triangle, and I maybe have ones in the main diagonal here, here, here. Not critical, but often useful. So I've eliminated below, that gives me the triangle shape. All right, what is the next shape I'm going to try to get?
The oval.
Diagonal.
Okay, so just the main diagonal. And how do we do this?
We need to get ones in this diagonal.
Okay, that's not the only part.
Zeros in the corner.
Okay, so zeros above, we eliminate everything above this main diagonal. So we did everything below. We kind of went, again, it doesn't need to be, but often left to right, easiest way to think about it. So we did this one, eliminate down, this one, eliminate down. We got to this one, that's left to right, and then we repeat. Start here, eliminate, use this one to eliminate everything above. And then go to the next position, eliminate everything above, and keep working our way back to the far left, and then it's finished. Then we have, at that point, if we don't yet have ones on the main diagonal, then we can just very easily scale down and turn these into ones, and then we get our solutions. So 1 times X is equal to this thing, whatever it ends up being. And 1 times Y is this one, 1 times Z is this one. So that's how we see our solution. But the 3 shapes, we start off with the box, and then move to the triangle, and then to the main diagonal. Those are the 3 shapes. Okay, we'll go through an example with this. Sorry, forgot I had this slide. We'll just show you the shapes one more time here. So box here, and as a matrix, this is the system that we did in the previous class. So here's the shape, box and box. And then as a system of equations, we can kind of see that triangle shape with the zeros below here, although it's a little more clear, I think, if we look at it as a matrix. But exact same things represented here, all the same numbers, top and bottom. And then the final one, main diagonal, zeros everywhere else. So there, that's the progression of the shapes here. Okay, let's try to do an application question here. I'll give you just a few seconds now, just read the problem, and then we'll talk about how we can turn this into some math and try to solve it. All right, so what's the first thing that we need to do if we're going to try to solve this?
Make 3 different variables.
Okay, so define variables. Before we actually build equations, we need to just define variables. All right, instead of using X, Y, Z, let's be a little more creative. We have candies, cookies, popcorn. So I'm going to call these C, K, and P. All right, what does C represent precisely?
Boxes of candies
It is the number of boxes of candies.
sold.
It is
The
not.
price for 1 boxes of candies.
Okay, that's what we don't know. So we were told here, this is the number that were sold. That information was given to us. What we don't know is what's the cost. So this is why it's important to be really careful when we define these terms. So the cost per box of cookies. Sorry, this is candies. And then same thing, cost per box of cookies. And P, cost of cans of popcorn. Apparently, you can buy popcorn in cans somewhere. So CKP, it's the cost, the per unit cost of each item. All right, we have variables. Now, how can we build equations from these? Can someone tell me what one of the equations would be?
2 C's plus 3 K's plus P equals 65.
And where are you getting that information from?
From the second sentence.
Okay, so this Amy person, this is the sales data for Amy. 2 boxes of candies, 3 boxes of cookies, 1 can of popcorn, total sales $65.
Now we're gonna
Right.
build the same for Brian. So
Yeah.
4 C's plus 6 K's plus 3 P's equals 140.
Mhm. And
And
then
same for Paulina.
8, 8, and 5. All right, we have 3 equations and we're 3 unknown variables, and we've been able to build 3 different equations. So this is a very solvable problem. If there is a solution, we will be able to find it. We've been given enough information. All right, so let's do that. I have that written out here as just a system, and we'll turn this into a matrix. And if we do that, just write the letters in 2, 4, 8, 3, 6, 8, 1, 3, 5, and then our constants 65, 140, 40, and 250. You can tell I'm being a little lazier today by just using these sort of rounded parentheses for the matrix instead of doing the 1, 2, 3, 1, 2, 3 square brackets. Both are fine. Just remember, you can't use only vertical lines. Just vertical lines like this has a different math meaning. Don't do that one. Use either of these other 2, but not just vertical lines. Okay, so here's our matrix we want to solve. Can someone suggest a row operation that we would do to begin this?
Yeah, row. No, so our first target row is row 2, so we can row 2 minus 2 row 1s.
Okay, row 2 minus 2 row 1.
To get a 0 in the beginning of the second row.
Okay, so we're kind of choosing this 2. We're using this first position here, and we're eliminating down like this. And I think we can do another operation at the same
Yeah.
time.
We can row 3 minus 4 row 1s.
3 minus 4 row 1. And that will eliminate the 8 as well here.
Okay.
So notice that we have not needed, it's a 2, a 4, and an 8. Those will scale very nicely. There's no reason to turn the 2 into a 1 right now. We could, although we'd have, fraction here, maybe we don't want that. So there is not an immediate need to turn that first position into a 1. We can just do that later when it's convenient. But right now we're already able to eliminate, so we don't need to do that right now. All right, so I'll start writing this out. Take a moment and calculate what those 2 resulting rows will be. Okay, so what is our new row 2?
Zero,
Mm-hmm.
0,
0.
1,
Mm-hmm.
10.
And 10. Well, we got very lucky with that one. The first 2 variables disappeared, and even the third one, it already turns into a 1. So that's totally solved for that variable. Very, very fortunate. What's our third row?
0.
Mm-hmm.
Isn't it -1?
Yeah, -4.
This position?
No, 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 no. The other one on the second row, isn't it minus?
Here?
Yeah.
We have, so this position, we had 3 and then minus
Okay. I
2
messed up. I'm sorry.
times the position in row 1.
I messed up the places.
Yeah. That's all right. All right. So what is our third row going to be?
-4,
-4. Yeah.
4,
1,
1,
And negative
10.
-10. Okay. So there are those positions here. All right. What's the next thing that we would want to do with this matrix?
To get a 0 in the third row.
Sorry,
Maybe
I
swap the rows first.
wrote my label in the incorrect location. So we want to have the main diagonal to be 1s here. What looks like the easiest way we could sort of,
Maybe we can swap row 2 and row 3.
okay, so that seems like the easiest possible thing. If we don't have to actually do arithmetic or math here, then that will definitely save us some time. So first row, not going to change, 2, 3, 1, 65. And then our new rows will be 0. Nice colors. 0, -4, 1, -10, and 0, 0, 1, and 10. Okay, so that looks closer to kind of our main diagonal sort of shape that we want. And actually, this is our triangle shape. So we've already done sort of the first half of the elimination process. Again, we have a -4 here, which eventually we will want to change into a 1. But for right now, it's not really a big deal because we're going to now eliminate with this column. We have a 1, we can eliminate here, we can eliminate here. So we can move forward and we'll take care of the -4 later. Okay, so I will write this over here. All right, what are the next operations that we're going to do with this matrix? Row 3 is done. Row 3 is perfect. We're not going to touch it anymore, but the other 2 rows.
Okay, so subtract row 2 from row 3 and subtract row 1 from row 3.
Okay, so I'll just flip around the order of those statements. We'll say row 1 minus row 3 and row 2 minus row 3. We don't even have to multiply anything by anything. We're just doing some simple subtraction here. Okay, so what is our new row 2 going to be?
0,
-4,
0,
0,
Mm-hmm.
and
-20.
All right, -20. 20. So the 0, we had a 0 down here, so that will be there. This was a 0, so the -4 will be the same as what it was before. We had a 1 here, or this was the position we were eliminating, so it should turn into a 0. So again, once we do kind of the second half of the elimination after the triangle, it becomes a lot less work. The only real calculation is this final position, -10 minus 10. And then we get -20 here. I'm going to be lazy, and instead of rewriting this matrix again, just to scale that down, I'm going to say, let's do this and multiply the whole thing by -1/4. And that will give us a 1 and 5. And then we've solved for our second variable as well. Nice thing about matrices is we can kind of do multiple steps like this at the same time and still clearly understand what was happening because we have this nice convenient label on the side here. So we still, anyone else looking at this can know exactly what we did and they can check our work clearly. All right, what is our new row 1 going to be?
Mm, 2,
Mhm.
3,
3,
0,
0,
and
0,
55.
55.
55.
So again, that was a 0, so not going to change anything. Row 1 minus row 3, that was a 0, not changing. This is the position we were eliminating. So the only real math, 65 minus 10, 55. All right, and looks like we can finish off this matrix with just one more step here. Rows 2 and 3 are totally done. And what is the final operation we are going to do?
Row 1 minus row 2 divided by 2.
Row 1 minus,
Row
no,
2.
I think row 2 multiplied by 3.
3 row 2, because we are using this 1 here and we're eliminating the 3. So we're going to need to multiply the second row by 3 in order to eliminate that one. All right, so this was a 2 in the first position. 0 will not change that. That's going to stay the same. This is the position we were eliminating, so it should become 0. This was already a 0. That's not going to change. The
40.
only one we're calculating is going to be, what's our result here?
165.
40.
40. 55 minus 3 times 5. That's 40. All right, and I'm going to scale this down at the same time. So let's do this and say we'll divide by 2. We could write this as a separate step, but not necessary. And there's our solution. So this is telling us that our CKP triple here is 25 and 10. And it's pretty easy to just go back to our original equations and verify that, yes, that works out. So there's our solution. That's the cost of each of those things. So I know when I had to write this, I had to do them sort of 3 on the left and then the next one's in the middle here. But if you're writing this on a piece of paper, normally you just kind of go straight down in one column. And it's easier to kind of follow everything. It definitely looks cleaner than if you were to solve this with elimination or substitution. So matrices, we can do multiple operations at the same time, different rows at the same time, or even as we saw with this scaling here, even sort of multiple things to the same row at the same time, like this, and still be able to see everything that's happening. The real time save with matrices is comes in if you imagine you had a huge system with like 5 equations and 5 unknowns, then you could get your first position and then you could do 4 different operations, 4 different eliminations, all at the same time. And then you'd go here and then 3 down and then 2 and then 1. So you could do your huge system. 5 by 5 is huge. If you were to do that just with substitution or like regular elimination, you'd take up pages and pages of work. But with matrices like this, we could finish the whole thing in just 8 steps. So that's 1 matrix, 2, 3, 4, and then 5, 6, 7, 8, and we'd be done. So it's much more concise and clean and organized. Okay, if anyone has remaining questions about matrix stuff at all, please ask. Otherwise, we will move on. Okay, so next slide. There we go. So I talked about this with your class briefly. I'll just kind of go over it really quickly here again. If we have a system of inequalities and we are trying to graph them, what is our process here? So if I have this y is greater than x plus 4, first step is imagine that it's just a line, y equals x plus 4, and then we'll graph that line. And that would look like this. So slope is 1, so that means it's exactly 45 degrees like this, and our y-intercept is 4, so it will look like this. Second step is now we think about the inequality here, and are we shading above or below? This is a greater than, so we shade above. The other way of thinking about this is just choose a point, usually the origin here, 0, 0 is the easiest one. We substitute in those points, which would be 0 greater than 0 plus 4, 0 is greater than 4. Is that a true statement? No, it's not. So this origin point must not be included in this inequality. So therefore, it must be the other side that we shade in. So just testing any point will let you know where to shade in. So there's this. And we'll do the same thing for the second one. So I'll do a little fast. Sorry, not finished here yet. The last thing about our inequality is that it's a greater than, not greater than or equal. So we can't use a solid line here. We have to change this over to a dashed line, which I am drawing, but you can't see right now until I erase this. There. So that's the first one. We'll do the same thing for the second one. So y-intercept is 1, slope is negative 0.5. So that is a slope like this. And in the other direction. Not perfectly lined up, but that's okay. And we have a less than or equal here. So less than A means that we are shading below. And my bottom half of this red line is really not lined up well. And then the second half of this is that it is less than or equal. So not a dashed line, but a solid line here for this red line. So up to and including the line. For the blue one, it's up to, but not including the line itself. That's the area. Okay, so if I'll put in a nicer version of these drawings like this. So here's the two independently, but then what happens if we want to represent the system together? So this is a system of inequality. So I want the area where both of them are true. So let's say we have area 1, region 2, region 3, region 4. Which one is the solution to both of them?
Region 1.
1.
Right, region 1, because that's the only place where there is overlap. So it'll be up to and including this part of the red line, but then up to not including this part of the blue line down here. And again, I have a cleaner version of that like this. So this is the solution. This is the representation of the system of inequalities. Nobody's asked this time, but in previous classes, people have asked, is there an algebra way to represent this? Is there like a simple way? If we have a system of equations, we solve and we get like a point. It's just these exact numbers, like we had the 25, 10 for the system we just looked at. This here is the simplest possible way to represent this with algebra, because the solution is this whole big shaded area. It's not just one point. So we say it's the area below this line and then the area above that line. That's the simplest possible way to describe this whole area on the graph. So that is the algebra representation. The solution area doesn't have like just this number or something. Okay, so that was the easier one, and then I gave you a slightly trickier one for the preview question from last week. So let's draw each of these. We'll do these one by one here. I'll start in the middle. So all of these slope is 1 or -1, so very easy slopes to draw. Let's start with our x minus 2. So that's this line here. And in the other direction. And the next one, x plus 2. Slope of 1, y-intercept of 2. It's going to look like this. All right, and then our top one here next. So -x, slope of -1 plus 8. So that's going to go through here like this. All right, a little problem here. The last one, y-intercept is 12, positive 12, and I can't see that on my graph. So how can I draw that one?
Maybe just find the x-intercept instead.
X-intercept, that's a great idea. So if we convert this, this would be x plus y is less than or equal to 12. If we have an equation in standard form like this, how do we find the intercepts? How do we find the x-intercept very easily?
Make the y into 0.
Right, so just forget the y, just scribble it out, and x is 12. Done. So very, very easy to do. So our x-intercept is going to be 12. So we can use that and draw our line like this, slope of -1. Okay, and we have to shade these in. So we're not done yet. So let's go back to the ones in the middle. The x minus 2. Are we shading above or below that line?
Above.
Above, because it's y is greater than or equal. So we're shading above. X plus 2 above or below?
Below.
It's below, it's less than or equal. So like this, so far solution area is just this sort of band, this kind of thin, long band like this. For our our negative x plus 8, are we above or below?
Above.
That one's above. And for the last one, the negative x plus 12, above or below?
Below.
We are below that one. So we're trying to see the area that represents the overlap of all 4 of these at the same time. And that ends up being this, just the square here in the middle. That's the only area that matches or satisfies all 4 of the inequalities together. So it's a square. That's what I asked you to figure out for the preview question. What is the shape? And there was one more little bit because I didn't want you to just guess random shapes. I wanted you to show me you actually understood it. So what is the area of this shape?
8.
8. How did you calculate that?
First find the length of one of the side by using the Pythagoras theorem.
Okay, so Pythagorean theorem here. So 2 squared plus 2 squared, and then square root of that. So the length of one side here is square root of 8. And it's a square, so just that length of one side squared will give us our total area, so 8. We can also just see this on the graph here, right? Like we see this little square inside, and that has an area of 4. It's 4 little boxes in there, so that's 4 total. And then we also see a little half box here and half here. Each of those is 1/2. So together, those will be an extra 1. Those 2 together would be 1 more box, 1 more unit. And then same thing, 1 and 1 and 1 all around the side. So area is 8. So visually or with some algebra, we can figure out the area. All right, that's the basic idea. So systems of inequalities, it's the area that matches all of them at the same time. That is the only area that's a solution, not areas that satisfy at least one of them. It must satisfy all 4 of them together. Okay, so now let's put that to use in this topic that we call linear programming. This has absolutely nothing to do with computer programming. It's more like, think like algorithms. This method predates sort of kind of modern computers and the modern use of the word programming. So the word, some fancy terms that we're going to need, and I'll be defining these for you very soon. Constraint line, feasible region, and an isoprofit line. So we'll see those in just a moment, but just to let you know, we have some fancy vocabulary for this technique. So linear programming is basically an optimization method. So what's the highest profit for this situation, or lowest cost, or the most of something? So we have a big range of possibilities, like we see with this shaded blue area, and then which of the spots in that area represents the best solution. So that's what we're trying to figure out. So let's go back. We'll use a problem that we talked about 2 weeks ago, about the student who's repairing and then selling used phones and used laptops, and they can only do at most 50 units per semester, and they have these 2 goals, 3,000. I changed the second one, 4,500. So we'll use this problem. And first we'll talk about it in terms of a graph. So the same problem we had before, and we'll look at it as a graph and just understand what that looks like. And then we'll add some depth to this. Okay, so first, let's try to remember what we defined here first. What was our X and what was our Y when we solved this problem before?
Don't really remember, but maybe X is number of laptops sold.
Okay, so that's the important part. So number of laptops sold. In this case, it is sold. So we read the problem and we make sure we define our variables very carefully. And then Y was just the other one, number of phones sold. All right. What is the thing that is holding this person back? What is the thing that is stopping her from having infinite profit?
She could only sell at most 50 devices over the semester.
Okay, and how did we represent that with math, with the variables?
X plus Y is less than or equals to 50.
Try that again. Less than or equal to 50. So before we just said equals 50, but now we're being a little more precise and we'll say less than or equal to 50. So she can only sell at most 50 devices. We have a codependent situation. More of X means less of Y, or more of Y means less of X. So these are not an independent and dependent variable. It's not like here's our Q and here's our profit. This is a different style of question, a different way of looking at things. We have two different things where we can produce, and they are codependent. Okay, our fancy term there are, these are limitations, things that are some kind of restriction on what she can do here. Our fancy term for these for linear programming are constraints. So to constrain is to limit, so same basic meaning, but we'll call them constraints. And her goal, her objective is profit. So maximize, or for now, just profit. And how do we calculate profit for this scenario? It's up here.
Should create the system of inequations.
Kind of. There's a particular formula we can use to calculate her profit.
Total revenue minus total cost.
This is not a revenue cost situation. We have not been given revenue. We have not been given cost. Also, those equations are for when we only have one thing we are producing. There's just Q for one thing. Here we have two different things that we are producing. So that analysis isn't going to help us here.
Her profit is between 3,000 and 4,50.
How do we calculate? In terms of our X and Y variables, how can we calculate?
We multiply the average profit for laptop and phone for the numbers of laptops and phones.
Okay, give me we have the numbers in the problem.
75X plus 50Y.
Okay, that's our profit. So that's how we calculate our profit. That's how we figure out for our objective. It's how we determine how much we're making. And then what our two questions are, well, first of all, can we reach 3,000? And then also, can we reach 4,500? So this is the way that we did it before. We'll come back a bit later and see a different way of thinking about it. But for now, this is the way that we saw this before. Okay, so there's the variables, there's our constraints or our one constraint, and then here's also our objective. So profit, and then here's how we calculate that objective. All right, so let's put this on a graph and then see how we can All right, let's understand what this looks like visually. Okay, if we're going to graph this, then first we should, well, we need some information in order to graph this. So our first one, we had this x plus y less than or equal to 50. What's the easiest way to graph this?
Draw the negative x plus 50 line.
I'm going to say there's an even easier way. We have standard form. We can pull out two pieces of information and graph right away.
The x and y intercept.
Okay, so the x-intercepts and y-intercepts. For doing these linear programming questions, this method of figuring out, of being able to graph your lines is very useful and very quick. So I will strongly recommend getting familiar with this. What are the x and y intercepts here?
50.
Okay, so both of them are 50. Remember, to figure out the x one, we just forget the y. Okay, x 50. And then to figure out the y, just forget the x. Y is 50. Done. Okay, let's do these for the next one. The 75x plus 50y is equal to 3000. So x-intercept, I'm just going to forget the 50 here. So 3000 divided by 75.
40.
What is that number?
40.
40. Okay, and we'll do the same thing in the other direction. So forget the x, and 3000 divided by 50.
60.
That one is 60. So when I do these in my head, for example, if I'm thinking 3000, just no calculator strategies here. If I'm thinking this, maybe it's a little confusing. I think, okay, 300 divided by 75. That's maybe easier. If I still can't see that one, I might think, okay, well, 75, let's maybe double that. If I had 300 divided by 150, okay, that's 2. And then this one then must be 4. Then here we've just added a 0, so 40. That's what I go through in my head to figure these out quickly. All right, what is the last one, with our profit of 4,500, what are the intercepts? I hear tapping on phone sounds like calculators.
60.
Uh-huh.
And
90.
90. All right, another no calculator strategy here. The 75 and the 50 are the same. The only thing that's changed is we went from 3,000 to 4,500. What is the factor here? 3,000 times what gives me 4,500?
75 multiplied by 20.
3,000 times what equals 4,500?
Wow, sorry.
1.5.
1.5. 40 to 60. What's the scale there? What's the factor?
1.5.
1.5. 60 to 90.
1.5.
1.5. It's the same thing. So if we just see what the difference is between these two constants, so it was multiplied by 1.5, the intercepts, the x and y intercepts will also just multiply by that same amount. So we calculate the intercepts once and then just, okay, it was doubled, so just double everything. It's very quick to figure them out afterward. All right, let's graph these here. So our first one, our constraints here, we have this, so x intercepts of 50 and 50. And are we shading above this line or below this line?
Below,
Below.
Okay, how do we know that?
less or equal to.
Okay, but before we had a y is greater than or a y is less than, but this time we have an x plus y is less than or equal to 50. So maybe this, well, is it the x or is it the y that's less? What's a way of thinking about this?
Both of them.
Okay, so both of them have to be less. That's one way. We could also convert this so y is less than or equal to negative x plus 50. And then, okay, the y's must be less. Or just think, put in a point, our origin 0, 0. So if we had 0 plus 0 less than or equal to 50, 0 less than or equal to 50, that's a true statement. Okay, so we must be shading below the line. So we're shading this area here. All right, and we will graph our other two lines as well. So our one where it's equal to 3,000, we have intercepts, x-intercept of 40 and y-intercept, that's the wrong color, 40 and 60, and then we also have 90 and 60 like this. Okay, so those are the two profit line goals here. So that's the information. We've graphed this. Again, this being able to graph just using the two intercepts is very, very convenient. Will save you a lot of time. All right, let me erase this and show you my cleaner version. So here's our situation. We have these two goals. So can we reach a profit of 3,000 and can we reach a profit of 4,500? So the first one, can we reach a profit of 3,000?
Yes, we
Yes.
can.
Yes, how do we know that?
Because if we produce 10 or less what fonts, was it fonts, we can reach the profit by producing more laptops, I guess.
I want you to tell me how we see the solution on the graph.
Because on the
visually.
graph, the line which represents profit of 3,000 is in their area.
Okay, so basically the green line for 3,000 touches the blue thing. So it's inside the possible area of solutions here. So let's introduce our fancy terms here. So our orange line, which represents sort of our boundary, our limit, this is the constraint line. So again, constraint just means a limit. So it shows the outer edge, the most whatever, like we have some sort of limitation, it shows the edge of that limitation. And then the blue area is called our feasible region. Feasible just means possible. So the blue area is the whole area showing all the different possible solutions. So can she sell 10 laptops, 10 phones? Yes, she can. 10, 10, that's in the area. Can she sell 10 laptops, 30 phones? Yes, it's in the area. Can she sell 20 laptops, 40 phones? No, it's not in the blue area. So the blue area shows us our solutions. Can she do 20 laptops? Yes, 20 laptops, 30 phones. Yes, it's on the very edge of the feasible region, but it's still inside it. So it's on that line. The line is included. It's a less than or equal. So yes, that point still works. Okay, so that's how we look at the line and interpret it. And let's think about these green lines a little bit here. So the first line, as we just said, is representing profit of 3,000. So this is showing all of the different combinations of X and Y that give us a profit of 3,000. So if her goal was to make exactly 3,000 and then stop maybe, then, well, she could do that with 0 laptops, 60 phones would give a profit of exactly 3,000. It doesn't match this other limitation, but it is a way of reaching 3,000. She could do 20 laptops, 30 phones. She could do 40 laptops, 0 phones. She could do some other points that are in between like this. So this looks like 30 laptops and 15 phones would also give her this profit of exactly 3,000. So all the points on the line that we have called profit equals 3,000 give us a profit of exactly $3,000. And as you might guess, so the ways for her to make a profit of 3,000 that match her limitation, it's anywhere on the green line that's inside the blue area. That will give her a profit of 3,000. And then all the points above that green line and in the blue area will give her a profit of kind of over 3,000. So that little kind of very slim triangle shape there, that's the profit of 3,000 or more that matches our other limitations, that matches the selling time constraint. Okay, so profit 3,000, yes, it's possible. What about the profit of 4,500? Can she do that one?
No,
Why not? What do you see on the graph?
because it's not touching any of the blue area.
Right, so this green line, the 4,500 line, doesn't touch the blue area. There's no point, there's no combination of X and Y that are on that line, but also inside the blue area. So that profit is impossible. So we answered this question before using systems of equations, and we saw, okay, to get this profit, we'd have to do like a negative X or a negative Y or something, and that's not possible. So we saw it that way, but now we can see the solution, the same kind of solution, but using this graph and looking at the sort of overlap or potential overlap of our limitations and our goals. So these two green lines here, we call ISO profit lines. ISO is from a Greek word isos that means same. So it's the same profit lines because they're the lines that show all the different ways to get the same profit. So the name sort of makes sense like this. And then we could make a whole bunch of these lines for all different possible profits that we might want to achieve. Okay, so that's how we can see the solution here for this just visually. All right, so let's add a little bit more to this. So currently, you know, we figured out this profit of 3,000 or 4,500. That's nice, but we don't want to be trying to solve one by one like that, one at a time. That's a bit annoying. So instead, let's try to ask this question. How can she maximize her profit? So 3,000 is possible, 4,500 is not possible, but what's the best? What's the most? So we'll see how we can figure that out from the graph. One little thing I've added here. I know some of you probably are already thinking just do all laptops. Yes, but we want to understand some theory so we can look at a more complicated question next time. So I've added something here, which I'm calling the non-negativity constraints. Basically, this is just saying she can't sell like a negative number of laptops or a negative number of phones. That's not a realistic, like real world. We know that's not possible. So it's good to represent that in the math. Say, okay, X must be greater than or equal to 0, and same for Y. They can't be negative numbers. It doesn't make sense in our problem here. Okay, so let's take this. We'll go back to our graph. And we'll try to think about where we might find the maximum. Again, we probably know it's all laptops, but let's have a bit of a discussion so we can look at some deeper questions next time. Excuse me. All right. I have 4 points on the graph here, A, B, C, D, and we are going to consider each of these and which one could potentially maximize our profit. So we're going to have a more general discussion, not just for this case, but in a general sense. Let's start with points C here. So point C is not on our constraint line. It's not on our orange line. It's somewhere just kind of inside, somewhere in the middle of our feasible region. Will a point like C, just in the middle of the feasible region, will that ever be the best possible solution?
No,
Why not?
because there's a potential that she could sell more devices.
Right, so she hasn't maximized the X and Y. She can go up to 50, but with point C, she's done, we can see here, it's 30 and 15. There's a gap between the point and then the edge of the shape. She hasn't maximized everything. It's like if I have some company and I give 8 people some work to do, but then I have another 2 people who are just sitting and playing on their phones or like calling their girlfriends or their boyfriends or something. Like if I haven't given those people something to do, then clearly there's some degree of waste. There's a missed potential. So points like C in the middle and of the feasible region and not actually on the edge will never be the best possible solution. Not just in this case, for any example, any problem like this. Second one, point B. Point B is on the edge, but it is not in the corner. We have A and D on the corners here. It's just somewhere in the middle of a straight line. Is it possible for a point like B to be the best possible solution?
Yes,
Okay, tell me why you think so.
because you said that there should be non-negativity, which means
So
if we choose-
non-negativity is this. Non-negativity is why we didn't shade off to the left because that's a negative X, and why we didn't shade down here with a negative Y. So all of the blue area matches the non-negativity constraint.
oh, I'm sorry.
That's right. Anyone else have an idea?
I don't think the point B can maximize her profits because, I mean, it's feasible for her because it's on the selling line, right? And her profit will only be maximized at 3,000 because it's right on the profit 3,000 line. I think she can earn more than that.
Okay. How do you know that?
Because I see some of the blue region that is above the profit 3,000 line.
Okay, this region over here. Okay, all right, you got the right idea. I'm going to explain a little more theory, a little more background here. So point B, it is maximizing the constraints, the only sell maximum 50 devices. So we've done that part, but that doesn't mean that it's the maximum profit. It just means that we've maximized the constraint. So let's say we have point B, and then we have another point here that let's call that point E. And let's say we calculate the profit at point B, and we calculate the profit at point E. And we do that and we see, okay, point B has a higher profit. Point B is a better choice than point E. If point B is better, then what do we know about the whole area on the line that's in the same direction as E?
That the profit there will be lower than.
Right. Okay, it's lower. So it's a straight line. It's not curved. So if we take one step in that direction, sort of kind of up and to the left here, then if we take two steps, we're going to get the same degree of change, just sort of scaled up. So taking one step, if it's a straight line and one step gives us less profit, two steps is not going to suddenly give us more profit. We're going to keep going in the same direction. So if any point to the left of B reduces profit, then we forget the whole thing. We don't want any point that's to the left of B. All of those mean less profit. Those aren't great. All right, let's do the same thing, same thinking, but now in the other direction. Let's say we have another point here. Let's call it point F. Let's have another point here. Let's call it point G. Let's say I compare B, and F and G are both on the line. They're on the limit. Let's compare B and F. And we compare them and we see, okay, B is worse. F gives us a higher profit. Then what do we know about this whole direction down to the right?
That the profit there will be higher and higher.
Okay, higher and higher and higher. So if B is better than F, then straight line, same direction, same pattern, then G must be better than F, and D must be better than G. So if any point in this down right direction is better than B, then you don't stop at the next point, you keep going until you hit the end. So points like B in the middle of our line, the middle of a straight line, will never be the best choice. You find one direction that gives you a higher profit or lower cost or whatever your objective is, and then keep going till you hit the end. So that's a very long way of saying, for these kinds of problems, the best solution will always be a corner point. Forget everything else, like draw the shape first of all, so you understand the shape, and then only pay attention to the corners. Those are the only places where you could have a maximum result. So just from some theory, just from some general thinking, we know it's A or D. One of those two must be the highest possible profit. Forget everything else. We don't need to test every single point here. It's just one of those two. So corner points. That is the first part here. Okay, so now the harder question. Between A and D, which one is better?
D, of course.
Okay, how do we know that? Looking at the graph, how do we know that?
The first explanation is from your previous explanation. And the second one is because point D is above the profit 3009.
Okay, so it now is where we're coming into these ISO profit lines, and we have to compare them in that sense. So D is going to maximize profits because of the direction that profit increases in. So this is this is one of the two things that people find very confusing about linear programming. What direction does profit increase in? In this scenario here, what direction on our graph does profit increase in?
Direction to the point D.
What do you, point D, but starting from where?
Starting from point A or B, I'm not sure.
Okay, you're saying like this direction?
Yes.
Okay, so point B and point C. Point C is more in this direction. So C has a higher profit.
No, because it's in feasible region.
Right. So it's not that. It's not this direction. That's not the direction that profit increases.
It's from the line profit 3000 to the right to the line profit 4500.
Okay, I think you got it. Give me in how exactly will we connect those two lines?
A line that is like, I don't know the word in English, not perpendicular to the y-axis, but the opposite.
There we go. So perpendicular, we used that word before. Remember, 90-degree angle between the two. This is the direction that profit increases. It's not to the right. To the right just means do more laptops. It's not up. Up means do more phones. The profit line here, so 3,000 and then 4,500. If I drew another profit line, it would look like this. And if I drew another one, it would look like this. No, like this here. So write the labels here. The next one would be a profit of 6,000. Next one, profit 7,500. So this is the direction that profit increases, perpendicular to all of these lines. So the question of between A and D, which one gives us a higher profit? It's which point is more in this direction based on these arrows here. Is D further in this direction or is A further in that direction? And then from the graph, it's pretty easy to see A is below our profit 3,000. Again, considering these arrows, it's below that line. D is above that line, so it's somewhere above profit of 3,000. So D must be better because it is more quote unquote up relative to these arrows. So that's the tricky thing. Profit does not increase vertically upward, it increases according to these arrows. If we just kind of rotate everything, this may or may not help you. But if you want, you can imagine just sort of turning the graph in your head. And now we can see it a little more easily. Here are these perpendicular lines. A is the lowest profit of these 4 points. B and C are going to be the same. They're both sort of level. And then D is the, again, quote unquote, highest relative to these lines. So D is the best possible profit of these 4 points. So if turning it in your head, if that helps you think about it, then that's great. If not, we can just imagine perpendicular to these lines. So when we try to solve these questions, what we will be doing is we'll have just one profit. We don't need to draw like 100 profit lines, ISO profit lines. We'll just draw one, and then we'll just compare and say, what's the perpendicular distance for each of the points? Whatever our corner points are, and I'm drawing extra that are not corner points, just for clarity. What is the shortest perpendicular distance? Is A closest to this profit line, or is B closest, or is C closest, or is D closest? Okay, D is clearly the closest. That's the best one. It's the most, D is the most up, quote unquote, up in this direction. So profit or our objective increases or decreases perpendicular to our ISO profit line or our ISO cost line or our ISO whatever line, not just up or down on the graph. I hope that kind of makes sense. We only care about the corners, and then in the two corners, whichever one is closest to that function line is the best one. That's the answer. That's the thing, but it'll probably take you a class or two before you kind of fully understand and accept that. So we'll wrap up here. I will go over this point again and explain this again in our next class, but just take some time and do some thinking, like kind of rewatch in the video, rewatch my explanation of this, if that will help you. Also, some other practice questions up here. Our textbook, it's a general math textbook. It's not an economics textbook, so it doesn't have anything about linear programming. So there's a different textbook here, which I have some pages of already posted on our classroom page, which has a good introduction to what linear programming is. And it's exactly these pages here in chapter 2 of that resource. So the rest, just graphing inequalities, graphing systems of inequalities, some word problems with equations and matrices. That's all in these other sections here. And that's, again, all posted already on our classroom page. So linear programming is kind of a bigger topic. It's going to take us about 2 weeks probably to fully do. So please take some time, make sure you actually understand what's happening with those graphs and how to solve them. It's not just some little one-time thing. We're gonna do a fair bit with this.